So this talk will have the following structure. First, I will tell you what WisePizza is actually good for and why you should care. Then briefly, because nobody cares that much about the details once everything works, is how does it do what it does? And finally, move on to some advanced applications beyond the basics from the first part. So what is WisePizza and what is it good for? It solves a very common problem in analytics. That suppose you have an aggregate of some sort. For example, you have the total revenue for last quarter, or you have your average conversion rate on your website over the last month, or maybe your average revenue per customer, or your average revenue per volume, which is the take rate. And almost certainly, you want to go underneath the average number and ask yourself, which segments of the data, which regions, which products, which currencies, if you have different currencies, we're pulling it up or down comparing to the global average. And then as a next thing, you want to ask about dynamics. So what drove the change from one period to the next? Or what are the drivers in the difference between, say, one region and another region? And what's usually happens is you have a data set with multiple discrete dimensions. So things like currency, region, customer type, product, subproduct, and you can have dozens. And we assume that for each of those, that you have a row for each combination of those dimensions. And then for each such row, you have a total, for example, total revenue for this microsegment, and a size. For example, if you care about revenue per segment, revenue per customer, then the size would be number of customers. And the total would be total revenue per segment. And a strong assumption, we assume that both those numbers are non-negative. And then we want to ask, which segments' averages were most unusual? And before we had WisePizza, this would have involved manual drill down. So you do a pivot in Excel or your drill down tool of choice. You do a pivot by one dimension, look at the largest values. Have a pivot by another dimension, look at the largest values. Then you have to worry about the overlap of those two segments. It was a very cumbersome manual process. And now, however, then the question is, do we have to go through all this pain? And I went through several iterations to do this. This is actually iteration number 5 or 6 of the analytical approach that finally worked. And it's using WisePizza. It's as simple as this. So let me talk you briefly through what this does. First of all, the call is as natural as it gets, in my opinion. So you want to explain levels, you supply a data frame, and then you tell it which columns represent dimensions that you want to slice by, which column holds the totals, which column holds the size of the segment, and then you tell it the depth, which is how many maximum dimensions you want to combine. So for example, here max depth is 2. So each segment can constrain at most 2 dimensions. And you want to have the number of segments. Sometimes if you just want a quick, does anything stick out like a sore thumb, you want to look at 5. If you want to look at more detail, you might have 10 or 20. And then it just tells you, these are the segments that are most unusual, most different in terms of how much they drive the overall average. And the first column is the impact. That is, if we reset the average of this segment to the average of everything together, how much would that change the overall total? And this is the impact of the segment's unusualness. And then just to give you some reference, you also give the simple segment averages. Just if we average if we add up all the totals and divide them by all the sizes added up of this segment, what would be the average? And how does it compare to the global average? And the segment size to give some context. And that's all there is to it. And you see that some segments have 2 dimensions constrained, some have just 1. And it's just the ones that have the largest impact that are most unusual. And by the way, all the data used here is synthetic, and it's also the data set that was used to produce this is also contained in the WisePizza repo, so you can reproduce all this data if you want. However, this is already wonderful because this is can save hours of scrambling around. But this the next step is you want to look at the differences. So you want to see how much has our total revenue increased from one quarter to the next, and which regions or which subsegments of any kind drove this. And WisePizza can do that too. It does this with exactly the same interface. The only thing it does extra is a how argument, and I'll go into this shortly. So the most simple one is how equals totals, and that just does almost exactly what it did before. So we have the old total, we have the new total, and the waterfall chart represents the segments that have the biggest impact. And then the other is just there. This is all the other components which are not part of this segment, because of course these 5 segments alone cannot explain the full difference. And so this is everything else, and you can see what matters. However, we can do better than that as well, because if you think about it, if you have your change in, say, total revenue, then it could either come from you getting more customers in some segments, or from the customers just spending more per customer. And there are different stories, and the difference matters. So if we think of a total as being a product of an average and a size, then we compose the difference in totals into a component that comes from the change in sizes multiplied by the average of the segment, and the change in averages multiplied by the size of the segment. And so now that we've decomposed this total into 2 components, change from size and change from size change, and change from average change, we can introduce this as a new dimension, and we can decompose it. So the simple way to decompose it is we separately look at the changes from size, at the changes that come from size changes, and the changes that come from average changes. And maybe that's the simplest way analytically, but it makes it unnecessarily hard to compare the segments from the top to the segments from the bottom. So the next one, which in my opinion is probably the best option of the 4 that I'm presenting, is you just say change from is just one more dimension. You have all the dimensions started from, in this case, product, type, currency, and region, and so on. And then one more dimension, which is segment average. And then again, you have maximum depth equals 2. So a segment can constrain either 1 dimension, 2 dimensions. And you see that some segments contain the change from dimension, and some don't. And then the final way of using this extra dimension is kind of the intermediate between the complete split and just treating it as another dimension, which is this forces to have every segment to have this dimension. So for example, here you have, so each segment is either a change from segment average or a change from segment segment size. All right, and so far, I've been thinking about explaining about different ways of slicing and dicing a change in totals. Which is a very natural thing to do, because after all, it's the total revenue or the total volume or things like this, which usually make the top lines. However, a related and equally important question is, how do you explain a change in averages? For example, what drove the change in which segments or customer segments drove the change in the volume per customer? Or which segments were the main drivers in the changes in website conversion and conversion rates? And it's not quite the same. It's a very similar question, but it's not actually the same question. And here is how you can see why. As I said before, we assume that all the sizes and all the totals are non-negative. And then, if a segment size increases, then the total will be increasing because everything is non-negative, and if nothing else changes, segment size goes up, total goes up. However, if your segment size goes up, your average can either go up or down. And that depends on whether the average of this segment is bigger or smaller than the overall average. And so this is a slightly different question, but we can answer it with a similar function, which is just called explain change in averages, with exactly the same arguments, exactly the same way of calling it, exactly the same graphs. So that's what WisePizza does, or the basics of what it does. Now, I'm sure that you're curious, how does it do that? Can I trust the way it does this? And the first question we have to answer there, which is a surprisingly hard one, is what is an interesting segment? How do you define interesting? Because what you will inevitably encounter if you try to do this manually is that segments that have very unusual averages will tend to be small, and the smaller you go, the more wild outliers you can get in terms of averages. But at the same time, because they're small, they don't matter very much. So how do you define a trade-off between the unusual averages and large sizes that make the segment matter? And the trade-off we chose is that a segment is interesting to the extent that if we were to reset its average to a global average, how much would then the global average change? Now, that's not the only possible trade-off. For example, another trade-off, and in fact, one that occurred to me first, and I'm sure occurred to you first as well, is something to do with statistical significance. So saying, for which segments is the average statistically significantly different from the global average? Or something like this, where we're talking square roots and t-tests and similar techniques. Now, this also can be done, but we haven't done this yet because the number of use cases for just working with averages and means and totals was much larger. But if you have a use case for different definitions of interesting, such as the one with statistical significance, please do get in touch, and then we'll try and implement that. So how does it do it? It's the basic approach is embarrassingly simple. We define a dummy variable with for every possible segment that we consider, and then we do a lasso regression, and then we do a simple binary search on the value of the regularizer until we get the desired number of non-zero coefficients. And on those dummy variables which end up having non-zero coefficients are the chosen segments. So far, so trivial. Now, the devil, of course, is in the detail. Having this idea is simple. Making it work is, as always, hard. So we do calculate actually candidate dummy variables for all possible dimension value combinations down to the required depth. But as you can imagine, if you choose depth equals 4, so you can constrain up to 4 values from any dimensions you choose, that can easily get into hundreds of thousands of possible dummy variables. And we don't want you to require a compute cluster to run this. So we use a heuristic. And the heuristic is that we select 100 segments that have the largest naive average, 100 with the largest total, and 100 with the largest average times the square root of size. Obviously, there'll be some overlap between them, so we duplicate, and we end up with some 200 plus candidate segments. And now we'll run a lasso of the target, and there is another trick we had to use, which is because it's simple linear regression, it's very hard it's very easy to end up with non-intuitive results, where if segments partially overlap, then you can have a sign of the overlap, which is very different from the sign you would expect to interpret. So one additional thing we do is we force the coefficient signs to equal the naive averages, so the interpretation is clear. And then the biggest challenge was making it work on large data sets. So it'll work with data sets which are as large as your RAM will take, but even so, we try to make it as efficient as we can. So one optimization trick is we use pandas joins. We use pandas joins to generate the dummy variables to depth 1, and then we just multiply those to higher depths. We use sparse matrices, of course. We pre-select the candidate segment based on heuristics. And then finally, we also use singular value decomposition to reduce the number of rows without changing the solution. And I've personally used it on data sets of up to 1 million rows and with depths of 4 and 5. And it's obviously not super fast, but it runs and it doesn't crash around. So much for that. And of course, it's all open source. If you want to dig into the source code, you're more than welcome to. Now that you have the overview of how it works under the hood, let's have some fun with it beyond the simple business analysis. First of all, so far you've always assumed that your variables, that your dimensions are continuous. However, this might not always be the case. For example, you might want to segment your variables you segment your customers by their spend in the prior month. Or there's a bunch of other continuous variables that you can come up with. So what do you do then? The simple solution for right now is just to discretize them manually. So, for example, just say which quartile of the distribution of all the values is this number in, and so you discretize them, and then you call WisePizza. However, one thing that I'm very excited about is that we will soon plan to use the opt-binning package to choose the boundaries that maximize the information conveyed. So you choose the bin boundaries in such a way that the differences, that the averages in the different bins are as different as possible. Now, the other thing where you can let your imagination roam free is that the changes in averages can actually apply to any kind of ratios, right? I've talked about some simple and intuitive averages, conversions per site visits, volume per customer, or maybe revenue per volume, but you can do much more fun things with this. So here is just one simple example, is you can explain the change in growth rates for one period to the next as the difference in ratios of totals. So not the change in revenue that we could already do, but the change in growth rates. And if you just set your size and as certain totals and your totals as the difference, then the explained changes in averages will explain the segments which drive the change in growth rates. And if you come with other creative ideas along those lines of what kind of other ratios can we look at that are not trivial, I'd love to hear about them. Now, even more fun. As some of you might know, especially those who follow my LinkedIn account, this is not the only library we've open sourced. The other one, which we're quite proud of, is the causal tune library, which is automated tuning and selection of causal inference models. And one application of this is that they allow you to estimate the impact of an A/B test at single user level. Not your typical techniques will just give you averages. The average impact of doing the variant is an extra percentage point of conversion. But with causal inference libraries, You can have pointwise impact estimates, of course. But pointwise effects are quite hard to work with, because then you have one number per customer. So what? But now you can combine it with WisePizza, and that can give you simple segments in which the A/B test was most effective and least effective. And that can be quite simple and quite powerful. And below is the link to an example notebook of which does exactly that. And now an application from data science. When fitting a model over a large data set, quite often you want to know where is the model performing poorly. For example, if you have some kind of a forecasting model, you forecast volume per customer, and then a month later you look at actuals versus forecast, then what you don't want to happen is your business users come to you and say, oh, the model did really poorly today for users in France. Why? And the first time you hear about it is from them. And so what you want to happen is for you to come to them and say, well, the model does really badly for iPhone users in France, and here's why I think it does that. And WisePizza can at least allow you to automate the first half of that. Also, they can get more fun. Namely, when you can have a very large data set, sometimes it's helpful to split it into several subsets and train one model for each. And sometimes that gives you better performance than a single model, because a model that's constrained on a well-chosen subset can be forced to focus on that subset's features and therefore perform better. And now this here is not proven yet. This is an experiment that we're currently conducting. But the promise of WisePizza is that it could allow you to do so in an adaptive fashion, where you first run a model over everything, and then you identify simple segments where that model does the worst. And you split those out to fit dedicated models. And potentially also what you could look at is you take the segments where your model did the best and split them out as well. So your model could focus on on the data that's left, on doing as best it can for the data that's where the performance is not so good, instead of resting on its laurels and just fitting the ones where it works anyway. And I'm sure you can come up with any more examples. And if you do, I'd love to hear about them as well.